Okay, so just checking that we all watched this lecture, because I'm going to ask you the questions that were inside of it. Can we write a function that uses take while and drop while to split a sentence at its spaces? Did we all watch this lecture? You know, these lectures are kind of like dependent on the material that comes beforehand. Please go watch this lecture. I'll try to make this lecture and not be too dependent on these questions, but I'm going to grab some. So the thing that you should have learned by watching the last lecture was that there's a bunch of functions defined on lists, specifically take while and drop while, which are kind of while loop-like. So therefore, maybe something that you want to use, and that we can use list comprehensions. And list comprehensions are quite important. Okay, so I want to do something called, I want to write this. I want to write a function that takes a string with spaces in it and then decomposes it into a list of its words. I think this is actually called words inside the prelude. We have words and unwords, but let's just do it ourselves. Okay, so last week we learned about these two functions, take while and drop while. So let's go into the system. We look at take while. Right, it's something that takes a predicate, a list, and returns a list. So we should already have some sort of notion how to use this. So I can take while, I'll make it a little bit bigger. Take while, I'll give some predicate, I don't know, bigger than the character A. I'll give it a string, A, B, C, D, E, F. What the hell is this? Ugh. And this is going to take from this string while everything is bigger than A. Oh, this is a bad example. A, B, C, D, E, F. How about this? So take while the letters are bigger than A, nothing. Take while the letters are bigger than less than A, nothing as well. What is happening here? Oh, A is not less than A. Take while the letters are less than D. And then I expect here to get A, B, and C. Okay, I can do the same thing. I can drop while less than D. And this is going to give you the rest, right? So one accumulates from and keeps, and the other one discards. Okay, so given these two functions, I want to write something called split. And split takes a string, and it returns a list of strings. Okay, so let's start programming. The easiest thing is, what's the smallest string? What's our edge case here? That seems sensible. So how do I split the empty string? Well, this is it. The idea is that if you were to join the members of the return list using spaces in between, that you get back the target. So this is it. It's empty, right? You generate an empty word by taking the concatenation of all words in here. What now should I do here? How can I use take while and drop while? Okay, what's one other case here that would be interesting? Well, we're searching for what? We're searching for spaces, right? And I keep prattling on about you don't take input and then ask what the composition of that input is. You pattern match that input at the point of definition. So what are we looking for? What's one interesting case in here where we're actually going to have to do something? Yeah, we detected a space. Okay, so we're here. The string definitely has at least one character in it. And I can say, actually, well, we can just say that's the empty string connected to the rest, right? So here is already like first character is empty string. Right? I didn't grab it and then test it and then dispatch. I'm saying here is what I want you to do when you've matched this pattern, when there is an empty string. Okay, so wait, that should be this. Sorry, yeah, you're right. I've confused empty string with I've confused the space with the empty string, which is something I yell at my undergrads so often about that I think maybe that I put the confusion back in my brain as a result of that. Sorry, of course, this is better. Okay, so this now says, so what happens if we detected a space here? What do we want to do? Yeah, we don't use it. We sort of, at this point, just have to throw it away. So what is the answer here? Yeah, I'm just going to assume split's working. Okay, go ahead. Just forget about the space. Split the rest. That's all I have to tell you to do here. Okay, so here, I'm going to split the inputs. So we're assured at this point that y actually is what? Not. But I actually don't care to separate it like this, because the only thing I want to look at that's a single thing is the space. right? So now I have the whole thing. So here, how do I use take while and drop while here to get what I want? Yeah. Yeah, take while. I always screw this up. Not equal to space. Is that the right slash? Or is it the other one? Oh, I always screw it up. Okay. It's like a what? Is it the same slice as not equal? Okay. Take y must, it's upside down in Canada. So take while from this. And then what? Okay, so what I get here, what I get from the first part here is everything that's not a space, and then it stops at a space. Right, so now what? Okay, so I also want to drop while not equal this space, but then what has to happen to this? I have to split on that. Exactly. Well, let's see. I'll try loading it. Should this be that take while? Oh, wait, hold on, let me think. Huh? This? Yeah, I'm trying to think. So this is going to this should return a string. So I think plus plus is appropriate here. Oh, right. Sorry. Yeah, that should be this. Oh, no. Okay. Either I can make that a list in itself. You're right. I should just use the cons operator here. This is going to return a list of lists. This is a single list, so I have to connect it to the list of lists, not concatenate it to the list of lists. Thanks for that. Okay. Because I want to split this. So if I take that out, then drop while is the function is going to go to split first and everything is going to be screwed. Right. So this allows me to drop a set of brackets. So I often just do this even when it's not necessary out of habit, because my functions more run naturally. You can always remove these things. So use the force, Grogu. There we go. See? But again, I just want to say we have words and unwords. Right, that like put it back together. Right, so these are prelude commands. Okay, so that was, so we gave you something that's while-like now. Right, so please use it responsibly. Don't try to use it all the time now that you have some type of imperative style loop. So there's the answer. Use list comprehension to define concatenation of lists. Whoops. Well, I'm sure none of you saw it. Right, so I want to concatenate two lists. Concat. And these are fun types of problems. I'm saying I have two lists and I want you to return a new list of those two, right? So I want to be able to say 1, 2, 3 plus 4, 5, 6. Can you solve this problem if the only tool I've given you is list comprehension? Concat. Okay, so just using list comprehension, how can I solve this? What does list comprehension do, right? It allows you to grab elements out of a set. So we're going to have to use list comprehension to grab everything out of X's and everything out of Y's. So let's think about this. Okay, so I want to grab something. Let's call it Z. And I want Z has to be drawn from X's and has to be drawn from Y's. So when I do something like this, I'll say, well, Z, you draw from Z's. And Z's, you draw from here. It may be in the wrong order. Let me change this. Is it the wrong order? It's really hard teaching in two different programming languages where all the rules are different. So I hope you guys can forgive me. I'm close. I'm usually like, it's either this way or the other way. Okay, so this is what I said here. I said, this will concatenate the lists. Concat 1, 2, 3, 4, 5, 6. Works as perfectly. What would happen here? Oh, I think I have to overwrite concat because I think concat was in the prelude. No. Oh, I reload. Okay. Concat's in the prelude. That's what happened there. But see, this is kind of clever. Right? I said we need to touch every element in both x's and y's. How do I do that? Well, I can touch every element in z, and I can touch every element in z repeatedly. Okay, so for those of you clinging to dear life to the imperative paradigm, here's your for loop. This is about as close as I can get you to for looping, right? But just don't over rely on it. But it is useful to occasionally use a for loop, right? With this trivialized solving the Cartesian product that we're doing last week. It prevented us from having to write one of those loops. So do add list comprehension to your arsenal of functional programming tools, because this is one of the important ones that actually port back to Python. Like we have list comprehension in Python, and that's all been set up so we can utilize the same patterns that we're learning in here. Okay, so that was a fun one. There's the answer. So I'm going to ask you two questions. They both can be solved with list comprehensions, but one of them is going to thwart us. This one is the easy one. Compute the list of naturals less than 10 that are divisible by 3. This can obviously be done with list comprehension. Okay, so let's see. Let's just write one statement. What did I say? List of natural numbers less than 10 that are divisible by 3. So that's x, such that x is drawn from 0 to 9, so less than 10, and x is divisible by 3. So what's our mod operator? Is it this? I think we also have mod. Mod 4, 2, that should be 0. Yes. So it is divisible by 3 when this is true. Null. I think null 0 is a thing, or maybe not. Maybe I'll just do an equivalence check here. It's easier. So when this is equal to 0, that should be true. Okay, so let me just take this out. Okay, and what? Oh, sorry, x2. Oh, divisible by 3? Okay, well, Jesus Christ, look. Morally the same. Okay, so they're all up. So it's very easy for us to say, I made a collection of numbers between that are less than 10, greater than 0, and divisible by 3. That was easy, okay? Compute the first 10 numbers divisible by 3. Now what? Huh? Yes, that's the answer. But I want everyone to understand that this is fundamentally different than the thing that we did before. So what do we do now? What do we do in our paradigm? Huh? Yeah, that's the answer. So why don't we generate all the numbers divisible by 3? We can do that. So let's do that. What are all the numbers divisible by 3? Well, that's at least one of them. Okay, so these are numbers divisible by 3 that are less than 9, right? Isn't that all of them? Okay, but what happens if I put that into the system? Okay, well, I can't do that. I just want 10 of them. How do I get the first 10? Oops. Do you see how different this is from the imperative paradigm? How do we get the first 10 numbers divisible by 3? Generate all of the infinite numbers divisible by 3, and then take the first 10 of them. That sounds weird, right? That would be crazy in the imperative paradigm, but that's the answer here. Just generate all of them and take the first 10. Why? Because we're in a lazy system. It's not going to generate an infinite number of these numbers. But this is the mode shift that we all have to start thinking about. I'm allowed to generate infinite structures and then take finite stuff from them. And often this is going to be the answer. In your magic homework, was this useful? You need to count something in one of your magic things, can't you? Can't you just pass it the counting numbers? But how many counting numbers? Well, all of the counting numbers. Right? So one of your magic solutions should be getting past an infinite list. That was the answer for that one. So regarding to magic, this is not something that we invented to torture you guys. Shh. We're going to start learning about higher level patterns quite soon. Like the way that we've been Haskell programming now is not even the simplest way that we can be doing Haskell programming. I'm going to introduce some higher order patterns that are going to simplify even further the way that we can write things. So really what we do in functional program is program with higher order patterns. And what we've done is I say, I know of one of the higher order patterns you will eventually learn. That higher order pattern can trivially implement the other three things that we asked you to implement. The question here is discover the higher order pattern and getting you used to this notion that we can use one function to solve a category of problems. Okay, so you should have discovered some higher order pattern in magic after giving up on trying to subvert the learning objective by asking if I can pass magic the identity function. And yeah, of course you can, but you've subverted the learning objective. So yes, not this year, but it was in your year, right? The last year. Last year it was scanned. The year before that it was fold. There are plenty of higher order patterns that we can test you on, but this is how we're going to test you. I know what pattern magic should satisfy. I'm going to solve another problem using your magic that should solve properly, if implemented properly. That's how we're going to check that. Okay? So just keep that in mind. So yeah, differences of philosophy, right? So in Haskell, you generate all the things and then you take a finite many of those things. But this should be something that you have to think that you're allowed to do. I'm allowed to generate all of the things. It doesn't matter that we have infinite stuff in Haskell. We never look at it. If you're using things, every time I see code put on the EdStem with length in it, it's like getting punched in the face through the screen, right? See, because like if we gave you an infinite structure, length now becomes semi-computable. You are playing with fire here, and why do you care about the length of something if you're just recursing, right? If you're using length, you got to ask yourself, why? Why am I using length? I can't fathom a reason you'd have to use length to solve any of the problems, right? Because really, like we really only care if it's empty or not empty, right? We just care about the pattern being head, tail. Was that it that I wanted you to learn from that week? Okay, yeah. So this is really the punchline of last week, which is why I re-emphasize it. Sometimes if you want a solution to something, you generate the solution to everything and just cut off a finite slice of it. You can get a lot of utility out of doing stuff like this. Go back and watch that lecture, please. Right, this stuff depends on the week before. This is why I was so tilted when the fire alarm went off. Okay, recursion. Finally, we got to talk about it. Right. So more of this. Okay, so I know it seems crazy that I'm talking about recursion now. Right, we've all been struggling with some type of problems. So the reason I teach this now is because I think now the class is actually receptive to hearing this lesson. Right? Now you're all like, how do I program in Haskell? I've tried and it's hard. Now teach me. Okay, so you're now ready. You now understood that the problems that I gave you weren't as easy as they ended up looking like. I think maybe next time I'm going to give you the number of lines that my solution has. Not to like flex, but just to give you not only to flex, but in addition to flexing, if I say the solution that I have has 4 lines in it and your code has 100 lines in it, I want you to be like, this is wrong. I've done this wrong. I want everyone to strive to find the shortest solution. Flex on me. I want you to be like, I got a 1-line solution for this. Vlad has 1-line solutions for all of your homework, which you understand is technically possible. I can take any of your code and make some extraordinarily long lambda calculus expression, which is 1 line. So it's not technically that impressive that he did it, but I'm still impressed. What I'm impressed by is like the shortest lines, like the fewest lines of code that are like still expressive, that I understand what's happening. I'm sure Vlad's code is going to be incomprehensible, but still impressive. So you should know that my solution to what's the words? Is that what it's called? Count words? 4 lines. That's and 2 of those lines are edge cases. Huh? 4. I have 4 lines of code for my count words. And it could have been 3 actually, because my count words just has 2 branches. So I could have replaced that with an if expression. And again, 2 of the statements are edge cases. So really only 1 line. I think once you see the solutions to your homework, you're going to be less angry with me. Right? Because you're going to see, it's like, oh, you didn't teach us how to Haskell code. I'm like, your homework doesn't require Haskell coding. It requires like several pattern matches and recursion. Okay, so this is why today I'm going to talk to you about actual strategies and how we think about these problems, because now that we've struggled a little bit and understand that imperative solutions will not work here, we'll onboard the lesson. Yeah. As long as you're okay giving a 100-line solution when a 4-line one exists. Yeah. In terms of grades, it doesn't matter. But in terms of your dignity, I'll leave that up to you. Okay. But does that mean if the 4-line solution exists, that's the easy, like if you write 100 lines, you've made your life a hell of a lot more complicated than it needs to be. Furthermore, you have to perform this on an exam. You're not going to be writing hundreds of lines of Haskell on the exam. You need to, one of the strategies for passing coding interviews at companies is to write as little code as possible to solve the problem. Okay. And every year, people email me after taking this class saying, I went to a coding interview and I was the only candidate to make it to phase 2 of the coding interview because I was the only candidate to identify the inductive question as having a recursive solution. And therefore, I was the only person to give a solution to that. That count words problem could easily be a programming question for you at an interview. And there's going to be 2 groups of candidates. The one group that gives the 4-line perfect solution, and the other group that flounders for a while that eventually, if lucky, produces a greedy solution, in which case the person interview is going to say, yeah, this is Google. This is not going to fly. You can't be writing greedy algorithms to solve stuff like this. Okay, so I want you, because like, look, we're getting saturated with programmers. Have you noticed? This is not even the whole class. I teach 1,000 software engineers every year. Actually, every term. Right? So I'm actually pumping out 2,000 software engineers. Okay? Market is saturating with okay coders. We need to make you better. We need to get you to that higher plane where you're like, I can do the imperative style stuff and I can do the recursive style stuff. I can solve both of these styles of problems. Hire me. Okay? We need to upgrade you a bit. You need to be programmers plus, right? Or whatever modifier Gen Z is using now. Okay? You're going to tell me what modifier Gen Z uses. Yeah. Okay. Is it hard to get complexities? We don't even care about that in this. Because in truth, everything gets optimized in compilation time. So that's where we have to talk about speed and stuff like that. Oh, yeah. But so complexity is, you just need to know the master theorem, and then you can get the complexity of anything that's recursive. Right? It's easier to get complexity of recursive stuff because it all just becomes, well, it's dependent on the complexity of the thing underneath me. But we don't care about complexity in this class. And like that's presuming you already have an answer, right? So that's quite presumptive, right? It's like, would you even have produced an answer in this case before getting to the complexity case? But the point is, there's categories of problems which can only be solved recursively. We need you to be comfortable using that tool set. Right? And the reason I picked Haskell is because you are obligated to use recursion. There's no other way of programming in Haskell besides doing it recursively. If I did this with Python, how many of you wouldn't have violated functional purity if I allowed you to do this in Python? Yeah, like 0 of you, right? So I forced you into this position. It's going to make us. I'm going to help you access problem-solving strategies that are going to put you in a higher echelon of programmers, which we need to do because the market is getting saturated. Savvy? Okay, let's power up. Okay, so let's start with the most trivial example of recursion that we can talk about, and that's factorial. Everyone familiar with a factorial? What is the physical property that it is measuring? Be more precise. The amount of ways I can arrange something. Okay, I have a cup. It can be upright. It can be upside down. Pardon me? It's the number of ways that you can arrange n distinct objects, right? So therefore, how many ways can I organize how many ways are there to organize a set of 0 objects? Did you say you can't? No, it's here it is, right? It's the absence of ordering, so that counts as 1. This is why 0 factorial is 1. Okay, so this is what we're going to grapple with today. All the scary vacuous cases, right? Why should factorial of 0 be 1? Why should the product of the empty list be 1? Why should the sum of the empty list be 0? We're going to just keep grappling with the fact that vacuous cases can be kind of scary, but we need to go all the way to the bottom of our cases. Who's not using P0 as their starting point in their induction? You better be doing it for the first triangle. 0 tiles are required to tile that according to our specification. That better be the base case, because I want the base case of the algorithm that eventually you will implement for that induction to be the simplest base case. right? Here's the tiling, the empty tiling for T0, empty list. That's going to be the easiest thing to type. So for those of you listening to this after, if you're starting at P1 with a triangle that you put one tile on, that's not deep enough. I'm telling you, don't do that. You're going to lose a mark. Okay, so let's implement this, right? So first of all, let's notice that this writing something like this in math is almost exactly how it would get implemented in Haskell. This is why the mathematicians sort of like this Haskell programming language. So let's just implement it like this. The obvious implementation is to say, given a number, I'm going to pattern match factorial. I'm going to say fact 0 is 1, and the factorial of n is n times, this is a slice, the factorial of n minus 1. That's just exactly what I did on the slide before. Midterm style, final exam style question. Will this run? Does this satisfy type checking? Why doesn't it not satisfy type checking? What 0 is this? Yeah, there's more than that 0. It doesn't know which 0 to match. So remember we discussed this last week, that if you want to do pattern matching on a number type, you have to derive equality because numbers don't actually come with equality. So this is a small nuance. I just want you to remember, because this is a very frequent bug in people's code, because it seems that I want to work with numbers and it seems sensible that I want to pattern match on 0, but you also have to define equality. However, if I change the type signature here to not be the generic number, but the concrete type integer, is this going to work? Yeah, now we're fine, because now Haskell knows, oh, 0, the integer. That's the thing I'm trying to match. Okay, so we can either keep it as a number or constrain it to the integers. It's usually better to keep it more general, because then we have a factorial function that's more portable. There are now some nuances in how Haskell pattern matches. We cannot pattern match on the num types without equality, because 0 is polymorphic. That is, 0 can take on many types. So Haskell doesn't know if the symbol 0 means the 0 int, the 0 integer, the 0 double, or 0 for any new custom data type that you may have defined. This is from the 2010 Haskell report. Matching a numeric character or string, literal pattern, against a value succeeds only when they're equal. So it's not actually doing a string comparison in this case. It's doing a unit comparison or a quality comparison. So this is why we necessarily need a quality type. So just keep in mind, the number class does not provide equal. It's kind of strange, but it's true. They're disjoint. Okay, so I'm just going to add equality back in here. I'm going to spin up this function. What is fact of 0? Yeah, too easy. What is fact of 3? Yeah, because it's 3 times 2. And what's fact of 2? Well, that's 2 times 1. What's fact of 1? Well, that's 1 times 0. What's fact of 0? 1 by definition. 1 times fact of 0. Yeah, 6. Factorial of minus 1? That's not true. It's defined. It's certainly defined. Infinite loop. It's defined. It's just, it's going. It's just, so we don't really call this an infinite loop. So what's the problem here? We've like missed the base case. Okay, so if we see recursions as sort of like moving down and then hitting a base case, missing the base case, we call bottoming out. That's what it's called, right? An infinite loop means you've missed your base case. You're just searching for a bottom that you're never going to find. Bottoming out. So we're going to use that synonymously in this class, bottoming out and infinitely looping. So the bottom symbol is this the same symbol that I was taught to use for false, this upside down T, upside down true. And it's because it's sort of on the bottom. So the bottom symbol is a term in Haskell which refers to computations that are not successful. Calculations that bottom out fall into 2 categories: failing with errors or failing to terminate. Okay, so this is called bottoming out. So how should we handle like bottoming out, generally speaking? What are our options? And in general, well, we do nothing. We say, we spin up a bunch of preconditions. We use the Python approach and we say, it's your fault for using the function wrong. That's good. It makes our programs easier to implement. I'll probably use this in class for that reason, but it makes debugging really difficult, right? Because you don't know if preconditions have been broken and then you have to go search. I don't know. We can default output. I can say, rather than like spin out forever, I can say, look, just assign anything that's like degenerate in the factorial to 0. Just say that it returns 0. It's a nonsense answer for the factorial. So we can have default out. So the problem here is this hides errors. Like your code's not going, it's almost preferable to generate an error when the code isn't working than to have something assuming the factorial of something is 0 when it's not. Okay. So this just gives us an opportunity to use like an if expression to sort of go around this. We can use the error message error, which a lot of you are using in your homework for some odd reason. Sure, we never asked you to do that. You can include it if you want. I never taught you how to error handle. It's probably better to put undefined in for errors at this point, because you'd have to sort of explain to me why it's an error and not undefined. Yeah. There's some places where I said don't use undefined, like in principal types, because that totally trivializes the problem, because you can set every function to equal undefined. But it doesn't matter. We didn't tell you what to do in degenerate cases. You just assume that the function satisfies whatever preconditions we've said. Again, I don't care that you guys used the error. It's just I was surprised to see it because we never officially talked about it. The most appropriate way to address these types of failure cases in a functionally pure setting is to do neither or nothing of above, but to use the maybe data type. Remember, we have this maybe data type. This is a type that that adds one extra thing to your type. And it's called nothing. Right. So if we have any function that's non-total, we can always make it total by saying, let's use the maybe data type. And for all places where you don't have definition, we're just going to say nothing. And surprise, now you're a total function over your maybe type. But we've grappled with this a little bit in practical, and it sort of pollutes the code. Like we have to do pattern matching in, pattern matching out, and all this other nonsense. I will eventually show you how we're going to use applicatives and functors to like avoid doing any of that stuff. But that's going to come in the signaling adversity lecture. Each approach has its advantages and disadvantages. None of them is the right answer to this question. All of them are valid. All of them are done out in the wild. Let's do number 2 just for now. I'm going to say let's return 0 for negative input. So I can spin up this factorial function. I'm just going to add a branch or a guard that says if n is positive, then do this. Otherwise, just throw back this default error. Okay, so now it's total. So now fact of 1 is going to give us 0. Will this work? More exam style questions. Remember at the the first time I ever showed you Haskell programming, I was like, negation is a pain in my ass. It is not going to work because this is passing the negation function to factorial and then trying to pass 1 to that. So you really do got to put some brackets here in order for it to work. So either these brackets or these brackets would be sufficient. For which one? This one? Yeah. This is fact of like I don't want to answer this question because I have to think about it a bit. This is why I don't like negation, because it's like sometimes unary, sometimes not unary, right? So in this case, it's not interpreting. No, if, okay, so I can answer this question by saying ifs. If this is interpreting negation here in this case as, if it's interpreting the subtraction symbol as the unary negation, then the way that Haskell is interpreting this is factorial gets the function that is the negation operator. And then 1 goes to that. That doesn't make sense. So I have to say, no, go evaluate to the right of me first. And then this says, oh, okay, I am the negation operator and I must receive an input. And then I become -1, which is then a permissible value to pass to factorial. We could sort of maybe tie this together using a dot. We could try to do function composition with the negation operator here, but let's not get too sidetracked. Okay, so types of recursion. This is primitive recursion. And in order to give a strict definition, okay, dear mathematicians, in order to give a strict definition of primitive recursion, I need the whole year, right? This takes me a whole semester to derive properly. I'd have to teach you basically the Turing machine course to get to the strict definition of this. Okay, I can't give you a strict definition for this. In this class, I'm going to need provisional definitions, all right definitions, good enough definitions. This is one such case. All of the definitions I'm going to give you today are going to be good enough definitions for what we need. Please don't ask me to make them more rigorous, because it would take a whole semester for me to define properly what a primitive recursive function is. Okay, so for our purposes, if you have any function that goes from A to B, or like, integer to integer, something countable to something. This is called primitive recursion when you have some base case defined outright, not even a constant, not even arithmetic is allowed at this point. It's just equal to something. And for f of n, for any n greater than 0, you can define f of n minus 1 in terms of n and f minus 1. So again, a function is called primitive recursive if it has a base case, and you've used the function itself to define the function, right? This is the basic definition of recursion that you were given in 1001, right? We're mostly going to be doing this. So this definition is not restricted to the integers. It's sort of any enumerable type, but when I say primitive recursion, it's the simplest type of recursion. Base case, and you have a recursive call, okay? More generally, what we've been showing you, or what factorial was in this setting, was called linear recursion. And linear recursion is defined as such. A function is linear recursive if every invocation of the function calls itself at most once. Actually, to be primitive recursive and linear recursive, it has to call itself either once or 0 times. Those are the only options here. So that is, each activation of the function invokes at only one other activation. So this is why it's linear, right? We're just moving, right? This does this, does this, does this, does this. So factorial is linear recursive. Can anyone give me an example of something that's not linear recursive? Quicksort. Oh, because you have to do merge jump. Okay, yeah. Okay, so quicksort, which we're going to do at the end of this class, right? It's because you have to call quicksort twice, right? It's the things that are bigger than the pivot and the things that are less than the pivot. What's the easier example here? Yes, sir. Fibonacci numbers, right? So Fibonacci numbers, every number is the sum of the previous two numbers. So every invocation, function invocation that calculates a Fibonacci number needs to calculate 2 Fibonacci numbers. And those two things need to calculate 2 more things. Okay, so you see linear recursive functions have one call, and that seems manageable. We're just building up a stack and then leaving it. If you branch, that can you can blow up the grader, right? Because every call is going to become twice as big as the previous one, right? So we need to try and write linear recursive functions when we can, so we don't explode, right? I think this is probably one of the first classes we are going to crash the grade scope because you've utilized 100% of your memory allocation. And that's if you write a function that's not linear recursive, that branches, and you just let it go, right? So that's quite easy to blow up memory with the Haskell system. Okay, so remember, linear recursive functions are those that only call themselves once or 0 times. Here's some of the terminology required when talking about working with recursive functions. And normally what I say is that we're just going to trust the recursion. If you try and understand what the recursion is doing, I'm going to qualify that as reaching through the abstraction barrier, which is a no-no. We don't do that. Okay, so today and today only are we going to investigate how recursion works along the entire stack. And then we're going to put it away because I don't actually want to be thinking like this. I just want to I want to say, look, it works. If we really scrutinize this, it works. So here's exactly what happens when we call factorial. Maybe not in Haskell, but generally if we were to find a recursive function for doing factorial. So the computer calls factorial of 4. It spins up a stack in memory in order to do that computation. When doing that computation, factorial of 3 is called. That's a new function invocation. The computer built another call stack with new inputs, and the new input, it needs fact of 3. When fact of 3 resolves itself, it's going to say I am 3 times fact of 2. A new stack is made for fact of 2, where it says I need to calculate fact of 1. A new stack is made for fact of 1 that says I need to compute fact of 0. And fact of 0 is termination point. Nothing is required to compute fact of 0 because it just returns a constant. It returns 1. Okay, so this is, maybe you have to sort of see this as being upside down. Like as me building a stack of calls. And this is the problem with using recursion in systems like Python or in C. They're memory intensive. Right? Because I need memory for that. I don't need memory for the function once. I don't need one stack. I need as many stack memories for function calls that recursive thing has made. Right? So I'm not saying recursion is the be-all, end-all strategy. It comes with downsides, but I'm going to show you how to mitigate them today. Okay, so here's this sort of stack being built up. And more generally, this is called the winding phase of the recursion. Things are getting tight. We're preparing something to do a computation by winding it up, but it's all sort of ready to go. Okay, because like this is what's put into the system. I'm not saying this is getting evaluated. I'm saying this is waiting. We're building up this expression, right? And the expression keeps saying, I need you to go resolve these function calls before I can actually start simplifying this expression. Okay, so here we have a winding phase, which is on the previous slide, and we end up here. And then whatever system we've implemented factorial in will say, okay, I've hit the base case for this function. No more function calls are necessary. So now what I have to start doing is resolving all of these stacks. Pop, 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 pop. Okay, so remember that brackets here indicate order of evaluation. And as we were putting new computations into here, the order of evaluation was being set as well. So this says, well, what first gets evaluated in this expression? 1 times 1, right? So that's what happens. It says, okay, I finished calling, and now I'm going to evaluate what's left at the bottom stack. And I'm going to do that from saying 1 times 1 goes to 1, 2 times 2 goes to 2, 3 times 2 goes to 6, 4 times 6 goes to 24. And therefore, this is how factorial computed 24. And this is what actually happened, right? Calls up all of these stacks, and then it disappears them all. But I really encourage you to only do this enough so that you convince yourself recursion works. Do not do this for new assignments that we're going to give you, right? Because it's going to be too complicated to actually execute this. In an induction, what do we care about? That there's a base case, and that we can get from the nth step to the nth plus 1 step. You need to regard your recursions the same way. There's a base case, and I have a recursive step that works, and that's enough, right? It works for the same reason that induction is going to work. So when you say, well, how is this recursive call going to actually work? Who cares? By magic, if you want, right? But it works for the same reason the principle of mathematical induction works. And the reason you're not, or we're not trusting it, is for the same reason we don't trust induction, which is why I'm giving you like so many of them that you're going to be inductive experts. Okay. So the time complexity of this is O of n. That's actually identical to the time complexity that we would assume factorial should have, but its space complexity is O of n. And we definitely don't expect to need a linear amount of memory in order to compute n factorial. Okay, but there is a strategy where we can actually eliminate the winding, or we can eliminate either the winding phase or the unwinding phase, depending how you want to define it. But the punchline is I can still do recursion in O1 of space. Okay, so caveat here. We're not supposed to do this in Haskell for a technical reason I'll discuss in a bit, but we can do this in C and Python. And actually, this is a great way of programming recursively in imperative systems, because it eliminates the need for a stack. Okay, so I'm going to eliminate winding by using something called tail recursion. And I'm going to define something called a helper factorial. I'm just going to have a factorial function that takes one extra input. And that's going to be a cheeky way, actually, of holding state. I said we can't make state changes, but we can be cheeky about this. If I want to hold, I can actually designate one of the input variables as kind of holding state. Some of you may have discovered this, like you put a counting variable there or something like this. So that's what I'm doing now. I'm saying, okay, factorial, I'm going to give you an extra input. This extra input is going to hold the answer. That's where I'm just going to compute the answer. I'm just going to keep dumping it into the first input here. And when you reach the bottom of your recursion, just return this answer, the thing that we've been computing. Okay, I'm saying, okay, so there's my base case for factorial. And now how do I update this answer with this factorial function? Well, I'm saying, well, h factorial of n, helper factorial of n, is n times answer. Update the answer, and then call this again n minus 1. And we'll look at more about how this actually works. And then I can say factorial function is just this helper factorial function, and you start it off at 1. Right? Because let's just look, what happens if we call this so we've given answer 1. What happens if I call it helper factorial of 2? Well, it's going to say, well, I'm 2 times 1. And then this will go down to 1. So it's saying replace me totally with h fact of 2 and 1. And then replace me totally with h fact of 2 and 0. And then replace me totally with h fact of 2, 2. So I'll write this out. So fact of 0 still gets 1. Fact of 3 still gets 6. Fact of -2 is still broken. But I'll just say, okay, let's just assume as a precondition, we're not going to pass this function anything that's negative, that this will only work with 0. We'll blame the user for any violations to this contract. For our purposes, this is what we're going to define tail recursion as. A function is tail recursive or iterative if each execution of the function either is the base case. You've stopped calling functions. I'm saying here it is. It's this. You really shouldn't be doing even arithmetic at this point, but we'll discuss this later. But really, it should just be a base case. You say I am equal to this. Right? Something static, something constant, or one of the inputs, right? The function, so a function is tail recursive if the last call it makes is to itself. Okay? The last call that makes is to itself with different arguments, of course. So the last function call a tail recursive function can make is to itself. And really what we're going to do, like I'm claiming this is tail recursive. What is it doing? The only two things I do is return something constant, or like one of the input variables. I'm no longer calling functions, or I'm calling the function itself with different inputs. That's the only two things that I have done in this function. If you constrain yourself to those two things, you'll have a tail recursive function. So this is how it works. So factorial of 4 is going to call what? Helper factorial seeded with 1 with the input 4. What's going to happen here? Well, h of factorial of 1 and 4 is just equal to helper factorial of 4 times 1, 3. That's literally what was there. So this is the important part. I can literally replace this with this. No stack is required. It's just a replacement. Remember, equal means equal, right? So I'm saying this is equal to this, just plain equal. This is equal to this. This is equal to this. This is equal to this, which by definition is 24. And we're done. This was recursion where I didn't actually make a function stack and pop them. It was just doing in-place changes. The reason this is called iterative is because this is effectively the functional while loop. Some of you may get really attracted to using this style of recursion, and that's fine. This is one of the, it's good actually, because this is the one that's most portable back to C and Python. Any questions regarding this, right? We just had a function and I just replaced the function with like the same function call with different inputs, but that's literally all we did. Yeah? Yes. Yes. H-fact is tail recursive, but we can say factorial is recursive, like by going through helper factorial. But yeah, those, I don't want to get too down in the weeds, because morally what I want you to understand is that there's a technique for doing recursion so that you don't have to build a winding phase, right? Which is the reason that like the memory gets wasted. So you can see here, no unwinding required, no stack required. The time complexity is still O of n, but the space complexity is back to O of 1, which is what we want. Yes. Yeah, I get asked this question every year, and you'd think that I'd actually go look up the answer. So you're saying no? What's the counterexample? I'd have to think about this, but I think no. I think probably no, because unless you ask a more specific statement than that. For one, you'd really have to say, are all primitive linear recursive functions convertible to tail recursive functions? That may be different. So I'll have to think on that, or someone can think on that and post something to the ed.stem. Okay, so I'm going to ask you to do a tail recursion on the next homework. I think it's average. I want you to compute average, the average of a list of numbers in a tail recursive way. Harder than you may think. Next week's tutorial, we're going to do a tail recursion for reversing a list. So you got a little bit of practice there. I think last year I asked students to do tail recursion for variance, which is something very similar. But the interesting thing here is, I have to mention the peril. Okay, now that I've told you how to do tail recursion, you're not supposed to do it in Haskell. You're just not, because Haskell assumes that like, no, we've set up this system for doing primitive linear recursion. Like the imperative space is where you do the imperative style tail recursion. But Again, this isn't a class necessarily on Haskell programming. This is a class on giving you guys recursion as a tool. So I need you to be able to do some tail recursions. We're going to do it in this system, but I'm going to be very explicit that, yeah, technically speaking, we're not supposed to do tail recursion in Haskell for this reason. Haskell is lazy evaluated. So if I were to do this tail recursion, it works like this. So factorial of 4 calls this helper factorial. And I'm going to put these curly braces for Python saying I'm being lazy. I'm not going to compute this yet. In an eager evaluative language, this would just be made for at the point of those two numbers contacting. But in Haskell, no. So if I call this, then H factorial gets called with that lazy expression, this lazy expression, and returns that. Okay, so we didn't actually avoid winding, because now I've just returned up this winded, lazy expression that Haskell is now going to evaluate like that. Okay, so we just reintroduced the winding and unwinding. So I am being honest with you that, yeah, using tail recursion in Haskell is not a good idea, but we still need to learn how to use it, so I'm going to force you to do it anyways. Okay. Suppose we want to prove that our Haskell code we wrote is actually correct. Suppose you want your braking system to be certified to brake when you hit the brakes, right? I have a piece of software that's guaranteed to brake when you brake, and the Python programmer is like, we're pretty certain that this is going to brake when it brakes, right? Sometimes software verification is like good when you're writing software where people are literally in life or death situations. Like you probably want to certify all the code going up to the space station and stuff like that. Okay, so how then do we prove code works? Some of you are in program verification classes, yes. The term loop invariant means something to you, yes. Okay, good news. Program verification in the functional paradigm is super easy, provided that you're comfortable doing inductions, which is why we're going to drill you on doing those inductions. So suppose for the primitive recursive factorial, I want to actually prove it. So here's how the proof is going to look. And this is going to look strange because I'm going to have to mix mathematical notation with like programming notation. I have to be able to say factorial of n implements factorial of n. And I know that sounds aggressively self-referential, but hey, this is the name of the game. This is recursion. Everything is self-referential in this game. It's slightly different. I use the sort of math text here to emphasize that. No, this is something that the mathematicians developed, and they defined a set of rules and its behavior over in the math space. My claim is that I encoded it as a program, and that the thing that comes out of this program is what you would expect to come out of the mathematical computation. Right? So that's why I use the two different types of font to try to just sort of delineate between these two spaces. Because people would say, like, isn't this obvious? That's what we implemented. I'm like, but then prove it's the thing that you implemented if you're claiming that it's simple. Okay, so here's our proposition. My claim is that the following Haskell code actually has the property that if I give it n, an integer, that it computes n factorial, according to the definition that the mathematicians gave. Here's a proposition. I'm going to say Pn is the statement that factorial of n is equal to n times n minus 1, so on and so forth, down to 1. I actually used sort of the expanded definition here, but I'm still borrowing even the definition of product from the mathematicians. But this should delineate it enough. Okay, so that's my proposition. This is, if I don't see this as the first line of your proof for your triangle question, you're losing a mark. I want you all to look at the first line of your induction and ensure that you're defining P. That has to be the first thing. So here's the statement that I'm going to prove. Everyone agree? Base case, by definition, the left-hand side of P naught is factorial of 0. Factorial of 0 is 1 by definition. By line 2 is what I would say in my proof. By line 2, by definition, factorial of 0 is 1. 0 factorial is also 1, according to the math rules, which is equal to the right-hand side of P naught, and therefore the base case is established. Savvy? What do we do now? What's the next step in induction? I've spun up Pn, I've proved P naught. What's the next thing that we do? Assume Pn, right? So I'm just going to assume that factorial of n is n factorial. That's the inductive assumption, right? And if the inductive assumption is true, I'm going to show subsequent to the inductive assumption being true that Pn plus 1 is true. So what is Pn plus 1? Well, so Pn is a statement regarding the equality of something. So I can always talk about the left-hand side of what this is, right, of this equality. So the left-hand side of Pn plus 1 is factorial of n plus 1. Yes? That is equal to n plus 1 times fact given this. By the definition, by line 4 is what I would, line 3 is what I would say here. I'm just reading from the definition of the program. This is not my opinion. I'm saying that's literally what's that line for. And in Haskell, equal means equal. So I know that equal really is equal. Okay? N plus 1 minus 1 is n. Okay, and I want to identify something here. Every year people say, how much do I need to prove? Do I need to prove this? And the answer is technically, yeah, you would. But we are seniors now. So I'm going to give you a tool, but you don't get to abuse it. Okay? You can say I'm taking something for granted. This is so obviously true, I'm going to take it for granted. Okay, but I need you to say that out loud. Right here, I'm saying I'm just taking for granted that n plus 1 minus 1 is n. And that's sufficient. However, if you say taken for granted for something that needed to be demonstrated, that is certainly not obvious to everyone, you'll lose marks. So just be careful, right? You can use this for stuff like here. Yeah, I don't need you to prove n plus 1 minus 1 is 0. Do you want to prove that addition is commutative or associative? We can do that on the next. Oh, a lot of you want to. Okay, no problem. Next assignment. I'm going to do that on next. Yeah, you're going to do that next assignment. I'm going to have you guys prove that addition is associative. For the definition of addition, the piano definition of addition. Okay, so let's keep going, right? So I permit you to take some things for granted. Just be very careful using this weaponry. Don't use it on like the whole problem. So if I continue just making equivalences from here, how do I resolve this? Well, fact of n is n factorial by the induction hypothesis, right? And then what we're left with is n plus 1 times n factorial, which is n plus 1 factorial by definition. So what have I proved? Well, that the right-hand side of Pn is equal to the left-hand side of Pn, and therefore Pn plus 1. So, conclusion. Fact of n is equal to n factorial for any n and n by the principle of mathematical induction. Any recursive program is going to have a trivial induction, right? Because the induction has to work, because if the induction doesn't work, your recursion isn't working. If your recursion is working, you get an inductive proof for free, essentially. All right, so when I did my PhD dissertation, I really strove to define everything that I did recursively, knowing that in my industry, I was obligated to give proofs, certifications that the programs were working. I claimed to have computed some mathematical structure, and I needed to give mathematical assurance that that was happening. And to make that easier on me, I did everything recursively. Correctness checking for tail recursion. This is a tad more tricky because you do need to find, I said tail recursion is essentially a while loop, or it's iterative. So in order to do a verification on a tail recursive algorithm, you need a loop invariant. Right? So some of you know how to work with these loop invariants, but it's not too tricky. So the loop invariant is, so I'm saying, if we have a tail recursive function, it does two things. Either it's its base case, in which case I'm saying I am equal to one of my inputs, or I'm saying call myself again, but with different arguments. I'm a tail recursive function if the only thing I'm doing when I call myself, let me try again. I'm a tail recursive function. The only thing I do is call myself with different input to myself. Therefore, at any point in that tail recursion, you need to be able to take the inputs and construct them somehow to get the answer. That's all the tail recursion is doing, is manipulating its input. So we should be able to make that relationship explicit somehow by using a loop invariant. Okay, I'm going to show you how this works. So here's our tail recursive factorial again, right? I'm just saying I'm just collecting the answer into one of the inputs, or being cheeky here and remembering state. My claim is that at any point in the running of h factorial that this is true. I'm saying it is always true that the answer and n is that h factorial of answer of n is equal to answer times n factorial, where I'm using n factorial from the mathematicians. Again, this is why I'm trying to use different fonts. I'm saying the left-hand side is a Haskell computation. The right-hand side is some statement. It could be an English statement. It could be a mathematical statement. It could be a picture, right? But it's something. How do I construct the answer from the input? Okay. So my claim is that this is always true. And if this is always true, what's specifically true about the initial call? Well, I said the initial call was factorial is equal to helper factorial, where you're starting answer at 1. So if this is true, this means factorial called at h factorial of 1 is equal to n factorial, which is the thing that we want. So let's go through the proof here. So again, I am asserting that my assertion is that this is true at all places h factorial rewrites itself. So specifically, it's true at 1 and it's true at 2. So here we're calling the definition of h factorial. We must show that at each line, the following iteration invariant holds, right? I'm claiming h factorial answer and n is equal to answer times n factorial. That is the manipulation of its input that gives you the answer immediately. Line left-hand side of line 1, okay? So h factorial answer at 0, according to my iteration invariant, is answer times 0 factorial is equal to answer times 1 is equal to answer. Okay, let's check what's the right-hand side of 1. This is an equation. This is 1. This is its left-hand side. What's its right-hand side? Right-hand side of line 1 is answer. So is left-hand side of line 1 equal to the right-hand side of line 1? So we've verified that this is true at line 1. Yeah? Let's verify that it's true at line 2. The left-hand side of line 2 is this. According to my iteration invariant that I claim, it's equal to this, which is as far as I can take it. So now let's look at the other side. What's the right-hand side of 2? Well, it's h factorial of n times answer and n minus 1, which I claim is equal to this iteration invariant. So n times answer times n minus 1 factorial, which is equal to actually answer times n factorial, because I just moved that n into here. Is left-hand side equal to right-hand side? Yes. So our iteration invariant is correct. No matter where we call h factorial, this is invariant. This is an invariance on calls to h factorial. This is something that is always true, no matter where we are in our winding step. So thus our iteration invariance is correct, and thereby we conclude I'm saying factorial of n is equal to this helper factorial function when I give it an initial input 1, which means, according to our iteration invariant, that this is equal to 1 times n factorial, which is equal to n factorial. Okay? So on your next homework assignment, don't worry, I'm going to walk you through this process of defining a tail recursive function for average and then making it equal to the primitive recursive one. And then I'll walk you through the steps here of proving these things. But we're going to write both linear and tail recursive algorithms for average, and we're going to give proofs along both of those. Okay? Any questions about this? It's a little bit tricky. The whole thing comes down to finding this iteration invariant, which is kind of tricky. So we're going to try to give you guys a little bit of practice. For the one that you're going to do in tutorial next week, the answer here is literally reverse the list. Right? It's going to sound strange, right? But the right-hand side of this expression could be an English statement or a picture or an equation, right? So it's good. You're going to say helper reverse is equal to reversing this list, but that's kind of the point. You're asserting that your function is constructing the answer that you're trying to construct. I know it feels self-referential, but that's just the name of the game. Okay, so for our tail recursion, I've demonstrated that it's correct, but in order for algorithms to be algorithms, we need to verify that they terminate. So the termination checking here is fairly easy for tail recursive algorithms. What we need to do, in order to prove a tail recursive algorithm stops, we need to find something called the bound value. And the bound value is some measurement on the input, where that measurement has to be in all cases non-negative and monotonically decreasing, actually. So this gives an upper bound to the number of recursive calls that we can make before making the next recursive call. And thereby, if it's the number of recursive calls is always non-negative and always decreasing at every invocation, it has to hit 0. It's a monotonically, it's a positive sequence of monotonically decreasing integers that has to go to 0, has to. So note we are insisting on decreasing 3, 2, 1 and not the weaker non-decreasing 3, 3, 1. That's why I say monotonic or strict. If it was non-increasing, that's not enough. right? Because then it could just be two iterate at most two iterations, at most two iterations, at most two iterations. Okay, so what is the bound value here? What do we have in the inputs that is non-negative and always decreasing at every recursive call? N, this N. Okay, so my claim is that the bound value for this function is its input N. Let's check two things. Is the bound value always non-negative? Yeah, that was a precondition, actually. Is the bound value decreasing strictly? Well, let's check. The bound value of this is N. N is bigger than N minus 1, but that would be equal to the bound value of this. So it is. It is decreasing strictly and positive. And therefore, this tail recursion must terminate. Okay? So it's just a different style of recursion that I've taught you that avoids creating recursive stacks. It is very useful in things like C, because you're just overriding the same part of memory, right? This function call gets totally replaced by this function call, which gets totally replaced by this function call, which totally replaces by this, which is a base case, which replaces itself with one of its inputs. It's all in place. Consider the primitive recursive definition of exponentiation on naturals in Haskell. So here's how I can do power in a primitive recursive way, right? The power of anything to 0 is 1. The power of x to y is x times the power of x to y minus 1. How can we convert this to a tail recursion? Well, what I want to do is just spin up another. It's almost the same thing each time. You just get you get one more input, and you utilize that input to just store the answer, right? So I'm saying helper power, I'm going to have an answer. And if you're going to ask me what helper power at 0 is, I'm just going to give back the answer that I'm currently holding. Otherwise, helper power at answer and x to the power of n is just what's currently stored in answer times x. This is where I'm accumulating all of those products, x and n minus 1, right? So again, all this function did was either state that I am equal to one of my inputs, or I am equal to myself called with different inputs. Right? It's really like f is equal to f, and you're just are allowed to do stuff in here. It seems easy, but this is going to require quite a bit of thought when doing the average. It's not totally obvious how you're going to do this with average. Okay, so then I can just say power, the thing I actually want, is equal to this tail recursion, right? You just sort of define it through this helper function. What's the iteration invariant here? How can I combine these so that it gives me the answer immediately, instead of forcing this iteration invariance to be, instead of forcing the tail recursion to go all the way to the end? How can I combine answer x and n so that it immediately gives me the answer? Well, I'm accumulating the answer onto answer, right? So answer partially is storing the answer. What's missing? Like, suppose I'm doing this for 2 to the power of 8. Eventually, 2 to the power of 2 is going to be here. This is going to be 2, and this is going to be 6. So how do I combine those to get 2 to the power of 8? Yeah, it's the partial accumulation multiplied by, yeah, the rest, what you're currently missing. It may not make, yeah, you may have to sort of like stew on this a bit, but if you want, you can just go through each line of this and confirm that it's true. It's true at line 2, it's true at line 3. So it's true everywhere that this is called. But it is the case that at any given point in this computation, that this is going to end up computing this. So it is fine, and indeed the point that the right-hand side is using power, right? Because I'm saying there's some mathematical computation that we're trying to duplicate here. So I'm sort of obligated to use the mathematical description here, because that's what I'm trying to match. Otherwise, there'd be nothing to prove. I would just define power and say it's definitively correct, because that's how I defined it to be. Okay. So just very quickly, I'm just going to show you that we can certify that this iteration invariant works at every line. Does it work at line 1? Well, let's check. I am asserting that my iteration invariant for this tail recursion is the one that follows. It's just answer times x to the power of n. Is it true at line 1? Well, h powered answer x to the 0, I claim is equal to answer times x to the 0, which is equal to answer because definitionally this is 1. And the right-hand side of 1 is answer. Okay, so for at least at line 1, it's equal. Line 2, the left-hand side of this, right, is h pow answer xn is equal to this, right? That's how I've defined it. Nothing else to do. But the right-hand side, well, if I take these inputs and I take answer times x, and that becomes this. I take x, it becomes that. This n minus 1 becomes this. I get answer times x to the n minus 1. And if I take that x and I combine it with this one, you get this. Is it the case that the left-hand side of 2 is equal to the right-hand side of 2? That's true. And since I said power x to the power of n is equal to the helper function when I gave it the initial starting point as 1, and I know that this is always equal to this, then this is equal to x to the power of n when given 1. And therefore, power x to the n is equal to x to the power of n. And we finished. That's proved. Certified. Okay? So we're going to have to learn how to do inductions on recursions, the primitive linear style recursions. And we're going to have to learn to do this style of iteration invariant verification on tail recursive stuff. It takes a little bit of practice. Do the list one next week, but do not get fooled. You have to work out a recursive average routine. It just takes a little bit of arithmetic, right? But you do have to think a bit about it. Okay. The bound variable for this, fairly easy, n, right? We're never going to do more than n iterations and multiplications to do the x to the power of n. So I'm saying the bound value of this tail recursion is n. By our precondition, n is always non-negative, right? Because we're just taking positive powers. The bound value of this, if I claim is n, that's strictly greater than n minus 1, which is equivalent to the bound value of this, which is the right-hand side of 2. Therefore, the bound values are monotonically decreasing and positive, which we can conclude termination from. Yes, miss? No, because that's not a number. The length of the list can be a bound value, and that's often the bound value. But the list itself cannot be, because I said the bound value has to be a non-negative integer. That was the first thing I said about it. So you have to convert. I'm not saying you're necessarily going to find an integer somewhere as one of your things, but in the case of a list, it's probably length of the list is the bound value. I'm not trying to say it has to be one of the inputs. It can be some property on one of the inputs, but it has to be an integer to start, and a positive integer at that. But that's a good question. And again, the answer is just length. Just do one thing. Mutual recursion. This is kind of fun. So you can do a type of recursion where you're not calling yourself, but you're calling something else, and that something else is calling you. And I'm going to give you a problem next week which requires mutual recursion to solve. It's beautiful. It's a beautiful problem, right? And once you realize which two things should be mutually calling one another, everything is going to click into place. It's a great problem. But how can I get even how can I test if a number is odd or even? Well, I can say even of 0 is true. I know 0 is an even number. And I can say n is an even number if n minus 1 is odd. And odd, 0 is not an odd number. And something is odd when 1 less than itself is even. This will work, right? And mutual recursion is fine. And there are going to be plenty of places where we're going to use this mutual recursion. So it's like a little bit of a level up, right? To have your function call another function and then that function call back. But as long as they're always calling on something less than the initial input, that's fine. And in both cases here, you're calling on something smaller than yourself. So we can just trace this when n is equal to 4, right? So 4 is even when 3 is odd, when 2 is even, when 1 is odd, if 0 is even, which is true. So that's how that works. Here's something you can try at home, like write a mutual recursive algorithm for extracting the odd or even parts of a list, right? So give that some thought. Oh, the answer is there, so try not to look at it. Okay, so a little bit behind, but that's okay. It was a good discussion that we have. Okay, so now just generic advice and practice for doing recursion. It's going to fill the rest of this lecture with just practical examples of little individual inductive style recursive problems. And I'm going to give you again, because I think now you're ready to hear this, to onboard the information required for programming in the functional paradigm. So let's do this. This coffee, man, great. Okay, so did you know that we used to, I think I may have told you this, but we used to teach functional programming to first-year students as like introductory programming. We used to teach that here, actually, right? 1001 used to be a functional programming class. But this Hutton wrote the book that I'm loosely following, and he still teaches functional programming to first years at his university. It's okay, mate. We all get a little gas once in a while. Like, I don't think we should laugh. He made a farting sound, so I'm just being juvenile. Get a sense of humor, Gen Z. My God, right? Farts are funny. That's like my toddler. That's just information that's in his brain. I fart, he laughs. I'm like, I didn't teach you that, but that is the appropriate reaction. Okay, so this is the advice that Hutton gives his first-year students about programming in this functional paradigm. Define the type. This is always a good starting point because it's going to obligate you to be careful about what your function is returning. Right? So it tells you what you should expect to take in and what you should expect to take back. So define the type. That's usually the first thing. Enumerate the cases. Well, once you have the input types usually induce some type of edges. So if your input type is a list, you're like, oh, I better be somewhat concerned about the empty list and maybe the singleton list and maybe some other bizarre things that happen on lists that are too short or even lists that are infinite. Okay? Define the base cases. Well, again, once you have delineated your the domain, then you can find the things that are weird edges on those domains. And then define the inductive case. You just assume my function is already working on lesser inputs. And then somehow you have to figure out how to utilize that information to construct the answer at the relevant level. And then generalize. Look at your code and ask if higher order patterns can satisfy these things, or try to simplify it in general, do some type of refactoring. So this is going to come next week. Next week, we're going to start hitting all the higher order patterns. And we're going to start seeing our Haskell code shrink and shrink and shrink. Okay. So here's my philosophy of doing functional programming. I write the program. I'm writing a function f, and I just say, this function works already. I'm just going to, it's just working by magic. I don't care. Elves have constructed all the recursive stacks here. But I don't think how it works. That is inappropriate. I don't care. I just assume that it does. And using that philosophy, I'm just like, can I then? Because once you assume the function is working on smaller input, you've already reduced the problem to a simpler problem. We were talking about frequency dictionaries last week, remember? And I said, in order to build a frequency dictionary, really, you just assume that you can already build a frequency dictionary and then add one more thing to it. Thereby, we've taken the problem of forming a frequency dictionary and reduced it to the problem of updating a frequency dictionary. One of those problems is easier. One of the powers of induction is you're going to take a hard problem and immediately reduce it to a simpler problem that's probably easier to solve. Definitely simpler to solve. Okay? So this is what we have to, you have to start trusting your recursion works. The same way that you've trusted your induction hypothesis when you're doing induction. You do not think how it works. You do not try to write down the stack. You just assume that it works. I never want you to do more than one recursive call. You just assume it spits back what you're supposed to be getting. Okay? That's how, really, you have to trust it. You have to trust the recursion. Okay, so what we're going to do now is figure out how to work out some of these weird edge cases. So suppose I want to write a piece of code that takes the product of a list of integers. So what are the steps here? I've written the type. That's step one. The domain is list of integers. What are our problematic cases? What are the edges here? Okay, empty list. Okay, and then I can't think of any other degenerate cases in this case, so I believe that this probably breaks down into two cases. The input is empty. The input is not empty. Okay, so that's step one. I have my type. I've delineated the edges. Let's now just define the inductive case. Okay, so what should it mean? How do I get the product of x con x's? Well, I say, just assume you can get the product of the tail of the list. How does it do it? I don't care. It just does it. And it brings back the product of the tail of the list by magic. Okay, so now that product has faithfully returned to us the product of the tail of the list. How do I take that information and utilize it to get the answer I need at this level? Well, I'll just multiply it by x. This is a simple example. Okay, but that's how you have to think. Okay, don't think, well, how does product do it? We can, but it's just because it does the same thing that you're just going to rewrite to again and again and again and again and again until you hit the base case. And you're going to realize, oh, as long as there's a base case and I can get from one line to the next, it will work. And it's like, yeah, you've just discovered mathematical induction. Cool. Okay, that's why I'm giving you these induction things. Okay, so this is most of it, but what's the lingering problem now? Base case. What should we put in the base case? Why? That is actually the correct answer. Okay, so why do we put 1 in as the product of the empty list? And the reason is because we're human and these patterns are ours, so I get to define them. So let's define them sensibly. Okay, so here's how you can work out these base cases if they really make you uncomfortable, because I am forcing you to go down to them. I don't care if they make you uncomfortable. You got to get used to it. Okay, go to the level you are comfortable with, which is usually the very next thing after the empty list. I don't think anyone here would argue that the product of the singleton list should be the number itself. Okay, so if that's the case, if we can agree that the product of the singleton list should be equal to X, and I know that we've defined this in our induction or our recursion, what does product of empty list have to be? Okay, why is the sum of the empty list 0? Because that's what makes the pattern work. Why is 0 factorial 1? Because that's what makes the pattern work. Why is x to the power of 0 1? Because that's what makes the pattern work. I know that may be really unsatisfying, but it's like, but it's just a pattern. It's a pattern. So I'm just telling you what the first thing in the pattern is. This didn't sort of come down to us, but like gilded angels or something. Like, this is a human invention. Everything was sort of arbitrary. Power itself was arbitrary, if you will. Okay, so the strategy here for working out these weird vacuous cases, go to the first case that makes you comfortable, and then backwards work out the vacuous case. Because it may not always be intuitively clear what the base case should be. Sometimes this is necessary, right? So I think I have some which is actually necessary. Okay, drop. So there's a prelude function drop, which given a list and a number, removes that number of elements from the list. So let's build it. What's its type? Given a list and a number. Okay, so probably, oh, I should reverse the description. Okay, so this gets a number and it gets a list and it returns the list. What's the domain here? Well, actually, it's two things. Integers is the first position, lists are the second. What are the edges of those domains? Yeah, in this case, we're not going to be able to drop negative numbers. So there's some like presumed precondition that the first input actually has an edge of 0. And the other thing is the list, which always has the edge of at least the empty list. So at least these cases, right? 0 in the empty list. I don't think that should be there, actually. Well, certainly we have to check empty list. Certainly we have to care about what happens at 0. And then we have other cases. I know this seems bad. I don't even know why there's spaces here. Maybe something's missing. Anyways, I'll correct this. But certainly I care about 0 being in the first position. I care about empty list being in the second position. And then I care about all of the other cases that those induce. Okay, so what's the general case here? Yeah, so the general case is that n is not 0, because otherwise I would have checked that already. And the second position is at least one element. So this pattern match isn't going to throw anything. Okay, so let's just define this then. So, right. Okay, so maybe some of these edge cases are obvious. To drop 0 elements from the empty list, I don't think that requires much discussion. Still empty. To drop 0 elements from a list, well, that's just the list back. So probably already this pattern is redundant, because it's actually caught by this pattern. I'm not saying that, sometimes you write some Haskell code and have to look at it and permute some stuff and eliminate some redundant edge cases, but this will still work. What does it mean to drop n from the empty list? Well, it seems obvious too. It's just the empty list. Okay, so there's some edge cases. This one actually is redundant and could be removed. What about the general case? So remember, we're going to presume that drop already works on smaller lists. So how do I drop n elements from x's? Okay, how do I drop n elements from x con x's? Yes. To drop n from x con x's is to drop n minus 1 from x's. I just assume drop is already working and I use it. You see, it's the same pattern each time here, at least for these linear primitive recursive recursions. Okay, so that was drop. There's something called init, which is like the reversal of drop. You guys do that at home. It's effectively the same thing. So we'll skip that one. Okay, multiplication. Let's assume that we don't have multiplication in our system. All we have is addition. And let's pretend we don't know that 0 times x should be 0, because can anyone tell me why? Because it makes the pattern work, right? Good answer. But that's what we're going to discover here. You know that multiplication isn't a new operation. It's just recursive addition, yes? So we should be able to define multiplication recursively using addition. Very, very simply. Okay. What's the domain? What's the type of our multiplication routine? Let's keep it easy. Let's say maybe integer, integer to integer. I don't want to play around with these like number classes. Okay. What's the domain? The domain is integer cross integer. What are the edges there? And we're non-negative integers. We have that precondition. So what is the edge of the non-negative integers? 0. Okay, so 0 in the first position is a concern. 0 in the second position is a concern. Maybe. Okay, I'm not saying that they are definitely concerns. I'm saying we should think about these things. Right? These are the edges of the domain. General case. What is the multiplication of x and y equal to? You only have addition. What's the philosophy here? We assume multiplication is already working for anything that's smaller than this. How do we use that now to answer this question? Yes, I think, or morally correct. To multiply x by y is to add x to the multiplication of x and y minus 1. Well, how does that work? Who cares? It's the magic elves are sorting it out for us, right? But it's going to work. This will work. Find the edges now. We didn't define the edge cases. We don't yet know that y times 0 should be 0. Let's discover this. What's something we're comfortable multiplying together? Probably this. Yeah, I know that x times 1 should be x. I don't think anyone argues that. So if x times 1 should be x, then this means x times 1 is equal to x plus the multiplication of x and 0, and thereby the multiplication of x and 0 has to be 0. And it turns out that one is enough, actually, because as long as we're decreasing the second position, we only need to care about a 0 being here, right? This one's actually not required. Because the second input is always going to decrement down. It'd be way less efficient because I could do 0 times 10 million, and it will take 10 million steps to realize that's that 0. But it's still going to work. Correctness is the name of the game in our industry, not necessarily speed. So that makes sense. Let's do more. The power set of A is denoted PA, and it's the collection of all subsets of A. Letting lists represent sets. Let's not talk about sets. Let's just use lists. Write me a function that gives me the power set of this collection. Okay, I'm not even asking you to do it really. Let's just use our framework. I'm going to show you it falls out of the framework. What's the type? List to list of lists? Generically? Think harder. Don't think harder. That's the answer. I was thinking we may need equality, but that was a different question. Okay, good. Yes, you didn't get tricked by my losing my mind. Okay, so we're going to do this. What is the domain? Lists. What is the degenerate case or the edge of that list domain? Empty list every time, okay? General case, not empty list. What do we do now? We assume that we can get the power set of x's. And all we then need is to utilize that information to get the power set at this level. How do we get the power set at this level, given the power set of the rest? Well, how can I describe this? Yeah, that was a little bit harder to work out. I don't want to go down too much of it. I'm running out of time. Okay, so if you got to think about it like this. So we have the power sets, and I have one more element. So what power sets if you look at the power set of a collection of items, and you look at one of the elements of the set that you're making a power set out of. There's going to be the sets that it is included in and the sets that it's excluded. Okay, so if I get the power set of the rest of this, those are all of the sets that exclude X from the power set. Okay, cool. But then all I need is the ones that include them. So how do I get that? Well, with a list comprehension, I'm saying, okay, the power set of X cons X's is the power set of everything else. Those are all of the sets that exclude X. And then these, the ones that include X. And this will give us the power set. Now, you have to do the same backwards working here. The power set of the singleton element is what? Well, this one you sort of have to work out mathematically. So if you have a collection of elements, what's the way that you can construct the power set is by including or excluding each element in turn. And one of them is excluding all of them. So you better have, like, every power set has the empty set in it for that reason. So that's why we had to do this. You can also work this out by going from here, because if this Y's is empty, this will construct nothing. You need to be able to draw from that. So sorry I couldn't go more in depth about this one. There's other ones I have to do, but this one would be a good one to study and try to trace a bit. But the philosophy is this: the power set of the whole collection is the sets that don't include X added to the sets that do include X. And how do I get the sets that don't include X? Well, by recursing, and the magic elves sort that for me. Ha! 2 lines, okay? 2 lines. You believe me? Let's do it. Quick sort. This is the one I was getting confused by, because I'm like, how do we, well, what's the type for sorting? Well, you need to be able to induce order on the list elements. So we need an ordered collection here. Then you give me a list, and I return to you a list. Okay, so maybe I'll do this one in the REPL for a better punchline. So quick sort. It's going to take something with order induced on it. I'm going to take a list. I'm going to return a list if it's ordering. What is the domain here? Lists. What's the edge of that domain? Empty list. How do you quick sort an empty list? It's empty. Too easy. And this should always be easy. If it is not easy, if you are doing something at your base case, probably you're not deep enough, right? But go deeper, right? Find the more appropriate edge, because I want you to define the easiest edge cases possible. Can someone please describe to me how quicksort works? Does anyone know quicksort? Go ahead. Okay, take your list, take any element out of the list, collect all the elements that are bigger than the thing you took out, collect all the elements that are smaller, quick sort those. Okay, so we need what? A pivot. So I said pick any element. Can we pick the first one? Cool. Okay, so this is the generalized case. I'm going to pull out a pivot. How do I collect all elements that are less than the pivot? List comprehension. Yes. X such that X is drawn from X's and X is strictly less than the pivot. Okay. Then how do I get all the elements that are larger than that? Well, same thing. Yep. And then what goes in the middle here? Yeah, I have to put the pivot. No. Okay. Every year someone confuses this. I've taken the pivot out of that, right? I'm holding the pivot. There still may be things equal to the pivot in the remainder, and we still have to keep those. But remember, X's has the pivot removed. I've done that type of decoupling. Okay. Okay. But these aren't going to be what we're not finished yet. Yeah. Because what remains to do here? Quick sort on those. Okay. Actually, it's more appropriate to do this, I think. Okay. Let's cross our fingers. Hooray. Ta-da. How many lines? 2. One of them's the base case. So this used to be like the reason we tried to get people into Haskell programming or functional programs. Like, well, we can do this in 2 lines. Look how crazy it is. Well, you can now do this in 2 lines in Python, right? Because you have list comprehension, but you could literally basically do exactly this in Python, right? But this used to be the list comprehensions and all of these things used to be only in the functional paradigm. And you're seeing the concept sort of moving from one to the other. This is why we're here today. You're going to see more and more of this stuff come by. How much time do we got left? Okay. Okay, so there's, as I promised, quick sort in 2 lines. So those list comprehensions are fairly useful. Find the least integer in a list of integers. How do you do this? This one should be easier than the last one that we did, but what? Actually, this is a little bit more tricky. I didn't put a precondition here, yeah? Huh? Well, okay, so what's the difference between small int and big integer? Big integer is not bounded. Unbounded. Yeah, big integer is like the biggest integers that we can use. Integer, just integer. This is the machine data type, yeah? And the machine data type, if we look at what is an instance of, it's an instance of bounded. And what do instances of bounded provide? A biggest and smallest element. So keep that in mind. Okay. So I'm saying, let's look at a finite list of numbers, ordered numbers. What is the edge? There's no lists. Well, what's the type here at least? I'm trying to find the minimum number in a list of integers. So, sorry, you were right. Yeah. It's a list of integers and I give back an integer. Okay, so the edges in this case then would be empty list. We don't yet know what it should be, but the general case is easy, x con x is. So what is the minimum element here? What do I write? This should be very easy. We're assuming list min works, right? So I get the minimum element of the tail and it gives it back to you. And then I still have x. Now what do I do? Yeah, I compare them and return the smaller one. Okay, so that's something like, oh, yeah, give me the minimum of x and the minimum with the minimum of the rest of the list. Okay, so now we have to backwards work this out. What's the easiest case? Where's somewhere we're comfortable? Well, a list with one thing in it. The one thing should definitely be the minimum. No one would argue with that. Okay, so we know that the list min on the singleton list is itself. But this means the minimum of x and this list min have to be equal to x. Yes? Has to return x. Therefore, what does list min have to be? The biggest thing. Infinity. Well, how can we get infinity? Well, anything that's bounded has if you're bounded, there's an element that's your supremum. So that supremum is the infinity. So actually, I want this. We can't really do this, but for bounded types, we can. What should I put in there? What qualifies as infinity for your type because you're bounded? So this is the edge of this. Max bound integer. And that's how you get infinity for that type. This is how you get infinity for any bounded type. This is super useful. I was training some people to do Amazon coding interviews, and I told them about float infinity in Java. It basically eliminates edge cases, which is how they're trying to thwart you at some of these interviews. Right? They'll get irritated with you if you find elegant stuff like this. Happened to me when I went to Google. They're like, "That's impossible. That doesn't work." I'm like, "It works. Believe me." Right? How much time do we got left? Okay, maybe let's think through this one. I'm going to give you, do you know what I'm going to give you a list. That list has a bunch of sublists in it. So the sublists are those by you just sort of like, oh, it's the power set effectively in this case, right? So you just get to exclude all or none of the elements in it, right? So here's excluding all of them, here's excluding one of them, two of them, here's excluding two of them. So comprehensively, the subsequences of 1, 2, 3 are empty collection, all the singletons, all the things with twos, and the one thing with three. Determine if a list of integer contains a subsequence that sums to some target. So here I know that I can make the target 5. It's here. I know that I can also make 3 twice. This one sums to 3, and then this one sums to 3. So write me a program that determines if a list of integers can, if this is true or false, right? I just want to know if the target's there or not. So step 1, what is the type information here? Yeah, list of integers, that's the input. An integer, that's the target. Bool, that's the response. What's the edge? Empty list. And maybe 0 needs a little bit of concern, right? Because I can always make 0 by pulling out the empty list, right? So that should be an edge. General case, okay? X con x's, right? And k. So how do I solve the general case? Assume that you can answer this question already for the tail. How do we reconstruct the answer here? So the way that you have to think about this is, are we going to use this x or not? If we don't use x, this is easy. Then I just say it's the number of ways that you can, I can make the target in x con x's if you can make the target in the tail. That's easy. Okay, but if I use x, then what do I have to do in the tail? Yes, make the target minus x in the tail. Well, which one of those two did I pick? You don't pick, both, right? You either can make the target in the tail, or you can make target minus k in the tail. Either would be fine with me. There you go. Right? I can make this sum in this list if I can make the sum in the rest of the list, or I can make the sum k minus x in the rest of the list. And then what are the edges here? Well, I'll leave you to think about that. Okay, but we need to think like this. The amount of lines of code that were necessary for your homework, 10 maybe, right? Certainly some of the homework I solved in 4 lines, like this, right? I think I could have given this subsum problem and it would have induced 100-line solutions. This is very similar to your words, aggressively similar to words. So maybe you should rethink words with this philosophy and get it down to 4 lines. Yes, sir. Pardon me? Oh, no. Do you want me to? Because I don't have to put it there, right? Haskell would infer it anyways. I'm just putting it there to be a good programmer, but it's technically not necessary. But again, I can always make any Haskell program a 1-line lambda calculus expression. So it's shortest lines of code that are still expressive is the thing that I'm going to be happiest with. Okay? Everyone okay for tomorrow? The deadline day? Okay. Okay. Go onward, Haskell programmers. I'll see you next week, right? Oh, thanks again for the coffee. I think this really improved the lecture. So you guys, little investments go a long way in the quality of the teaching, right? I used to teach multiple sections of classes. That's what we did in Canada. I don't teach 1,000 students at a time. I teach maybe 200 students 5 times a week.